So welcome to my class on Anova. In this class, I will be talking about one-way Anova and two-way Anova, balanced and unbalanced. Okay, so we'll be considering the balanced data and the unbalanced data for one-way and two-way Anova. Just in case you don't know what Anova means, it is a statistic acronym for analysis of variance. So welcome to GER Hub. If you haven't subscribed to my channel, please endeavor to subscribe to the channel by clicking the subscribe button and endeavor to turn on your notification bell so that you can get notifications whenever we go live or drop a new video. That being said, let's begin. So in this particular class, I'm going to be looking at problems. I'm going to be discussing 4 problems, okay? Questions 1, 2, 3, and 4. Question 1 will be a problem on the one-way Anova balanced data case. Question 2 will be a problem on the one-way Anova unbalanced data case. Question 3 will be a problem on the two-way Anova balanced data case, and question 4 will be a problem on the two-way Anova unbalanced data case. So let's quickly jump right in. Now, please, just in case, if you have a pen and paper, you could quickly take down this question. The question says question 1, which is a case for the one-way Anova balance case. Question 1 says, in order to determine the effectiveness of a new brand of electrical appliance in the market, 5 products were selected for 5 research electronics, and the appliances applied with the following yields. So this is the problem we are looking at. Please take note that my rows will be representing treatments while my columns will be representing levels for the one-way Anova case. So the question demands that we test the mean yield, test if the mean yield of the electronics are significantly different at 5% level of significance. Please take note, to make it easy for you to understand how to go about solving a problem on analysis of variance, I'm going to be using 5 steps. I'm going to be using 5 steps, and I want us to take it step by step, just in case you are someone who may not understand if everything is all lumped up. So I'm going to be taking them step by step. So let's start with this problem. Let's start with our solution. So the first thing I'm going to do will be step 1. So what will my step 1 be? When you are given a problem like this, make your step 1 the statement of hypothesis. So step 1, I'm going to write state your null and alternative hypothesis. So that will be the first thing I'm going to do. So in the one-way Anova, there is just one hypothesis. That is one hypothesis in the sense that I'm merging the two, the null and the alternative, okay? Because in the one-way analysis of variance, what you are basically doing is to test for discrepancies or significant difference or lack of significant difference between the treatment means. So I'm going to now state, that being said, in my step 1, I'm going to quickly go to my null hypothesis. What should my null hypothesis be? Looking at this particular problem, you will notice that, like I've told you earlier, that there are 5 treatments: treatment 1, treatment 2, treatment 3, and treatment 4, and 5. So there are 5 treatments. I'm going to use mu to represent the means of each treatment. So I'm going to call this mu1 for treatment 1 is not equal to mu2, or is equal to mu2, equal to mu3, equal to mu4, equal to mu5. Now what this means, please take note, is that we are, in other words, saying that the mean yield of the electronics are the same. So we are, in other words, saying that they are not significantly different. Okay, that's what we are saying. Now, what we are going to do thereafter is to state our alternative hypothesis. So if your null hypothesis is saying that the mean yields are the same, that is, they are not significantly different, or what do you call it? The alternative hypothesis will be saying that they are significantly different. So in this case, I'm going to be using mu1 is not equal to mu2, not equal to mu3, not equal to mu4, not equal to mu5 to mean that the mean yield of the electronics are not the same. Okay, so that will conclude step 1. So the first step is state your null and alternative hypothesis. Once you're done with stating your null and alternative hypothesis in step 1, go to step 2, guys. So in step 2, the next thing to do will be to you would now have to define your critical region. So the next thing I'm going to do will be step 2, define the critical region. Now please guys, take note that the critical region is otherwise known as the rejection region. Okay, so it is the region in which the null hypothesis is rejected. So I'm going to say define your critical region or define the critical region. Here, what we shall be doing is we are going to state under what condition we reject our null hypothesis. So I'm going to say here, reject H0, okay? Reject H0 if your F computed value is greater than your F tabulated value. So if your F computed value is greater than your F tabulated value, reject the null hypothesis. This will be the critical region. Now, just to remark, your F tabulated for a one-way Anova such as this, how do you get it? So for you to get your F tabulated, all you have to do is to say F tabulated is equal to F treatment number minus 1 for the degree of freedom for treatment, and N, the number of observations, minus A, the number of treatments, at alpha degree of significance, or alpha level of significance. So now in this case, for our particular problem, please take note that F at A minus 1, we have 1, 2, 3, 4, 5 treatments. So my A will be 5. That will be 5 minus 1. And we have a total of 5 by 5 observations, making 5 times 5 giving you 25. So your N is 25. So that will be 25 minus your A, which is 5. And this will be at 0.05. Remember, you were told to solve the problem at 5% level of significance. So this would now mean finding the value of F, your F value at 4, 20 at 0.05. Now, I did a quick summary that will help us in this case. Now, I have already gotten the values. This is just an excerpt from an F distribution table in your statistical table. So I have already gotten those values that I need for these problems. So you will notice that F under the first degree of freedom, which is in this case 4. So if you trace down 4 for your V1, your first degree of freedom, and move down to 20 under 0.95, which is testing at 5% level of significance, you are going to have that value to be 2.87. You could confirm this value for just confirmation's sake, okay? So it means that the degree of freedom here will be 2.87 when you check from your statistical table. Now, that will conclude step 2. So I'm going to move over to step 3. What would I be doing in step 3, guys? In step 3 is where you compute. In step 3, compute your sum of squares. So compute your sum of squares. That is, By your sum of squares, we want you to compute the sum of squares total, that is V. We want you to compute your VB, that is variation between treatments. We want you to also compute your VW, in this instance, the error, okay? So we want you to compute this sum of squares, V, VB, and VW, okay? So that will be the next step you take. Compute your sum of squares in step 3. Remember, we are taking steps to solving this problem. So once that is done, in your step 3, the first thing you compute is your V, which is your V total, okay? And the formula for computing this is double summation of your xij squared from I equals 1 to A and your j equals 1 to B, where A is the number of treatments and your B is the number of levels. Now, you now subtract the summation of all observations from I equals 1 to A, the number of treatments, j equals 1 to B, the number of levels, all squared, divided by AB, the number of treatments times the number of levels. Now, if you perform this, this would mean, for this particular problem, this would mean summing every observation, the square of every observation. Now, if you go to your table, you would find that you have 22 squared plus 26 squared plus 34 squared plus, so if you add along the horizontals and proceed in that manner to the very last data entry being 26 squared, that is what you are going to have. Then subtract from it the total of all observations, meaning that you add 22 to 26 to 34 up to 26, you are going to have 668. So you could confirm these values all divided by 5 times 5, that is 5 the number of treatments and 5 the number of levels. This would give you guys 19114 minus 17848.96. Okay, so when you simplify this, you're going to get this result, and when you simplify this, you're going to get this result. Please confirm, and this would end up giving you, when you subtract, 1265.04. So that gives us our total sum of squares. Now, moving on to VB, for the variation between treatments, the formula we had was AB from I equals 1, J equals 1 to B, the number of levels. Remember, this is a one-way balanced problem for the Anova, and this will now give you summation, double summation from I equals 1, J equals 1 to B xij all squared divided by AB. Take note, this is your correction factor. Now, this simplifies to B summation I equals 1 to A xi dot bar square. Take note, this is simply because in this observation there is no J. So the J is more or less a constant. The J sees this particular variable as a constant, and summing it up over B, you end up having B times the summation of xi bar squared, okay, from I equals 1 to A, minus the correction factor, of course, this. So this is just for simplification's sake, to make you understand what is going on here. Now, all over AB. Now, to put in exact values, this is more or less saying 5, the number of levels, in brackets, times the square of the means. Now, please take note. Let me go back here. Now, look at this. The means in this case is the mean of each treatment. Remember, the electronics are seen as treatments. So we have treatment 1, treatment 2, treatment 3, treatment 4, treatment 5. How do you get the mean of each treatment? This is one treatment. Add 22 to 31 to 28 to 27 to 23. which will give you a particular value, and divide it by 5, because just take the average of these values, 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 and the average of these values, which is adding them up and dividing by 5. Now, that will give you what we are going to have here. So please endeavor to try that after now. So you would end up getting, if you do it correctly, 26.2 squared plus 23.0 squared plus 31.8 squared plus 28.8 squared plus 23.8 squared, okay, minus the value we have for the correction factor already. Remember, we had it to be 17848.96. So I'm going to bring down that value here, 17848.96. And simplifying, this would give me 5 times the sum of everything here, 3622.56. When you sum up all the squares here and multiply by 5, that's what we are going to have. We are going to have this. So I'm going to bring down this value. I'm going to bring it down and thereafter simplify. So when you perform this simplification, you are going to end up having, if you do it correctly, 263.84. Now, we are still under step 3. And remember, guys, step 3 is where you get the sum of squares. Now, I'm going to move over to getting my VW. So what is your VW? Your VW is the variation or the variance within treatment. And for you to get that, all you have to do is subtract your VB from your V. Remember, VB plus VW would amount to V, total variation. So what did we get our V to be? Remember, we got our V to be 1265.04. So I'm going to bring here 1265.04 minus, what did we get our VB to be? We got it to be 263.84. So I'm going to subtract 263.84 from this value, and that will give me 1001.20. So that will be the value I get from doing that. And once you are done getting all your sum of squares, we've now gotten our V, we've gotten our VB, we've gotten our VW. So what next? The next step you take is step 4. So what is step 4? In step 4, we will set up our Anova table. So in step 4, we set up our Anova table. So quickly, I'm going to set up my Anova table as follows. So what I'm going to do is this. Please take note, what should make up your Anova table are 5 major columns. 5 major columns for the one-way Anova and 3 major rows, okay? So this is what I'm going to do. Just watch what I'm doing. So this is, I'm going to split this into 3 rows, 1, 2, and 3. And I'm going to split this into the following columns, 1, column 2, column 3, 4, and 5. Okay, so I now have that. So what I'm going to do is, the first column is your source of variation. This is where you tell us where variation in the problem could arise from. Now, please, variation, guys, could arise from between treatments. Okay, so between treatments, you could have variation stemming up, and within treatments also. From within treatments, you could have variation, and variation could come from all the observations, so you have total variation. Now, the next thing is your degree of freedom. Your degree of freedom. Your degree of freedom in this case for the treatment, since there are 8 treatments, subtracting 1 gives you your degree of freedom. So A minus 1 is the degree of freedom for treatment, and that will be A, which is 5, minus 1, giving us 4. Now, for your within treatments, your degree of freedom will be N, small n, or capital N in this case, as the case may be, minus A, and this would give you the number of observations was 25, minus A being 5 gives us 20. Now, total variation is obtained, the total degree of freedom will be obtained by adding this to this, which gives you n minus 1. Please permit me to be consistent with my small letter n. So this is n minus 1, giving me 25 minus 1, which is 24. So 4 plus 20 gives 24, and that confirms that you are in order. So sum of squares is what I would come over to now, my sum of squares. Now, what were sum of squares? V, VB, and VW. So VB was for between treatments. So I'm going to write out the result we got for VB, which is 263 rather, 0.84. I'm going to write out the sum of squares we got for within treatment, which is 1001.20. I'm going to write out the sum of squares we obtained for total, which is 1265.04, and that completes the column for sum of squares. Thereafter, I'm going over to my mean squares. Okay, now how do you obtain your mean squares? The mean squares are obtained by dividing each sum of square by the degree of freedom. So I'm going to use 263.84 and divide that by 4. When you divide that by 4, the degree of freedom for between treatments, you are going to have 65.96. Now, when you do same for the sum of squares, dividing the sum of squares within treatment by 20, the degree of freedom, in this case, you would have 1001.20 divided by 20. That would amount to approximately, that's the 2 decimal places, 50.05. Now, here you put in the last column, which is F calculated, otherwise called F ratio, whichever one you want to call it. I prefer calling it my F calculated. So this would give me 1.318. Now, how did I get this value, guys? The way to get this value is dividing your mean squared between treatment by your mean squared within treatment. That is, this divided by this gives this value. Okay, so that completes step 4. Now, come over to step 5, where we conclude the problem for question 1. Step 5 is where you make your decision. Now, how do you make your decision, guys? You compare your results from the Anova, that is the F calculated, with the result you obtain for the F tabulated. So remember, for you to reject the null hypothesis, the F calculated must be greater than the F tabulated. However, if it so happens that your F calculated is less than your F tabulated, you do not reject the null hypothesis. So that being said, let us now see. Looking at our F calculated, I'm going to write here, I'm going to say, since F calculated is equal to 1.318, and this value 1.318, my F calculated, is less than the F tabulated, which is, if you remember, let's go over, what did we get our F tabulated to be? 2.87. Now, looking at this, you will notice that our F calculated is less than our F tabulated, 2.87. So, since this is less than this, which is not clearly the criteria for rejecting the null hypothesis, we would conclude that we do not reject the null hypothesis. Okay, so that ends the problem. Once you have your F calculated less than your F tabulated, you do not reject the null hypothesis. So guys, this concludes question number 1. And what was question number 1 again, guys? It was a problem on one-way Anova balanced, for balanced data, one-way Anova. So let's now move over to question 2. Now, for question 2 happens to be a problem of this nature. Question 2 happens to be a one-way Anova unbalanced problem. Okay, it's a one-way Anova unbalanced problem. Now let's read the problem together. A process engineer obtained measurements from 4 machines that produce a specific product to know how significantly different their diameter measurements were for each product. He took 5 measurements for each machine as displayed in the data setup below. Now the question comes, test the hypothesis that the measurements are not significantly different for each machine at 0.05 level of significance. So in this case, looking at our data, you would notice that some data, treatments, these machines are our treatment, guys. So all the machines, there are 4 machines, implying that we have 4 treatments, and there are 5 measurements, implying that we have 5 levels. Okay, so under each treatment there are 5 levels of measurements. So I'm going to start the problem again. I'm going to solve the problem again in 5 steps. Put them in steps, it makes it very easy for you to comprehend. So let's go over to solving this problem. So the first thing I'm going to do will be, like we did earlier on, state in step 1 your null, state your null and alternative hypothesis. Okay, so state them. Now, the null hypothesis, you could write mu1 equals mu2 equals mu3 equals mu4. Now, take note, these are the treatment means. How many treatments do we have again? 1, 2, 3, 4. So each of these treatments would generate treatment mean. So the treatment mean 1 is for treatment 1, the treatment mean 2 is for treatment 2, the treatment mean 3 is for treatment 3, and the treatment mean 4 is for treatment 4. So we want to verify whether or not there is a significant difference in the treatment means. So stating it this way implies that what you are, in other words, saying is the mean measurements are not significantly different. Okay, so that is what the statement means. Now, for the alternative hypothesis, mu1 will not be equal to mu2, will not be equal to mu3, will not be equal to mu4, and this is otherwise to mean that the mean measurements are significantly different. Now, please take note, the essence of setting up a null hypothesis is with the intention to nullify the assertion. Okay, we intend to nullify our claim. So once you've stated your null and alternative hypothesis, the next thing you do will be to go to step 2. So I'm going to move over to step 2. Guys, what are we to do in step 2? In step 2, you are to define your critical region. So I'm going to define my critical region. Define the critical region. Okay? Define the critical region. So here, we reject the null hypothesis. It is under defining the critical region, you tell us what condition, under what condition you reject the null hypothesis. Here, we reject the null hypothesis H0 if F computed is greater than F tabulated. Okay? So this will be the critical region. Now, I'm going to remark here where F tabulated in this case will be calculated as follows, or obtained as follows. It will be obtained with A minus 1, the number of treatment minus 1 as the degree of freedom for treatment, and N minus A, the number of treatments, the number of observations minus the number of treatments, okay, at alpha level of significance. So this will be F4 minus 1, because we have clearly 4 treatments, 1, 2, 3, 4, minus 1, 4 minus 1, and I'm going to have here a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 observations, so my N is 16 minus A, which is 4, at 0.05. So this will give me f at 3, 12, 0.05. And this value, once you check for F312, let's come over F312. Like I told you, I made this easier for me, and you could also check and verify. It is easier for you too. So go to your statistical table, check. There are 2 degrees of freedom for the F distribution. V1 is the first degree of freedom, and V2 is the second degree of freedom. So the first number, 3, is checked, and you move to 0.95 because we are testing at 0.05, okay? 0.05, 1 minus 0.05 will give you 95, and 95% is 0.95. So you check for 3 under 0.095 for 12, okay? And that will give you 3.49. So I'm going to put here 3.49. Now, this concludes step 2. What have we done in step 2? We have defined the critical region. So once I'm done with step 2, I'm going to move over to step 3. So in step 3, what do you do again? In step 3 is where you obtain, your, in step 3, we start obtaining our sum of squares. So I'm going to put here step 3. Now for step 3, we say compute the sum of squares. Okay, compute the sum of squares. That is, what are we computing? We are computing V, VB, and VW. So that's what we are computing. How do we compute V? V will be equal to double summation. Please take note, this case is an unbalanced case, so I'm going to use BL from I equals 1, J equals 1 to BL, okay? Because the levels are not the same in number. So this is that minus BL again, I equals 1, J equals 1 to Xij. Remember, I'm using BL as the limit simply because all the levels do not contain the same number of observations. So I'm going to put here all over n. Take note, no longer A, B. Now, this will be equal to, for this case, what would you do? You are going to, for this particular case, we are going to square the observations, all the observations. Let's square them. 20 squared, you would have 40 squared plus, it goes on up to 20 squared plus 35 squared, the last 2 observations, minus, you would have here, when you sum all the observations like we did earlier on in the distribution, you are going to have 612 all squared divided by n. The number of observations is 16. Now, once you do that, the next thing you do will be to sum all these. When you sum them accurately, you will get my value. So my value is 412 rather, minus 374544 for the square of this divided by 16, and that will translate to 27412 minus 23409. And when you subtract, finally, you are going to have 4003. And that will give you your V. Now, the next thing you do will be to get your VB. Your VB, the formula for your VB will be ABL, I equals 1, J equals 1. But this time around, it won't be Xij squared. It would rather be I dot bar squared minus the correction factor, same as above, summation A from I equals 1, J equals 1 to BL, Xij all squared all over n. Now, in this instance, you won't do the same routine like before. What you would rather do would be to use each level. Now, let's go over to the problem again. Now, I'm going to get the mean of treatment 1, 20 plus 40 plus 20 plus 60 plus 35 divided by 5, and use that the mean I get from treatment 1 to multiply 1, 2, 3, 4, 5, because there are 5 observations in treatment 1. I would do the same thing for treatment 2, 35 plus 40 plus 70 plus 20 divided by 4, because there are 4 observations here, and use that number, the value I get as the mean, to multiply 4. I'm going to repeat the procedure. 5 for this case, the mean times 5, the mean times 2. So that is what I'm going to do over here. So let's see. So if you do that, you are going to get this result. So this will be 5 times the mean of the first treatment, which is 35 all squared, plus the next will be 4, the number of observations in that treatment, times 41.25 all squared, the mean of that treatment, plus 5 times 43.4 all squared. Okay, you could bring this squared here, it won't do any harm. So then the last will be 2. For consistency's sake, let me do this. Okay, so this will be 2 times the mean of the last treatment, 27.5 all squared. Okay, minus the value we got earlier on, 23409, for our correction factor. So that's what you are going to do. Now, if you move ahead and simplify, simplifying this by adding everything and subtracting this value would give you 452.55. Now, that implies that our VW will be V minus VB, which will be 4003. Okay, if you compute accurately, minus 452.55. This will give you the result 3550.45. So that concludes our step 3. So what did we do in our step 3? We got all our sum of squares. I will now move over to step 4. What are we going to be doing in step 4? In step 4, as usual, you put up your in step 4 you put up, or you set up, your Anova table. So that being said, let us quickly set up our Anova table. Again, I've told you, like I told you earlier on, that your Anova table contains 5 major columns, and for the one way Anova, 3 major rows. Okay, aside the header row. So I'm going to do this quickly. I'm going to do this 1, 2, and 3 rows, and I'm going to come over here and put 1. I need 5 of them. 2, 3, 4, and 5. So those are 5 columns. So first header will be sum of well, it will be source of variation. Second will be degrees of freedom. Okay, the third will be sum of squares, and this will be mean squares, and the final will be your F computed or calculated, whichever one you want to call it, or F ratio. You will still be right. Now, once you do that, under source of variation, variation can come from between treatments. Okay, variation can come from within treatment. So this will be within treatment variation. And variation can come from all the observations. So I can just put here total variation. Now for degrees of freedom, here you would have A minus 1, which is in this case 4 minus 1, giving us 3. There are 4 treatments, so you would have 4 minus 1 degrees of freedom. For the observations and within treatment, you have N minus A, which is N in this case is 16. So 16 minus 4 will give you 12. Now for the total variation or total degree of freedom, you're going to have N minus 1, which is the same as 16 minus 1, giving you 15. Okay, so clearly 3 plus 12 gives you 15, and that tells you that you are correct. Now for the sum of squares, just quickly bring the values we have 425.55 was what we had for our variation between treatments, okay? Then I'll bring the one we had for within treatment, 3550.45 here. I'm going to bring it here, 3550.45. For the one we had total variation, I'm going to bring what I had, 4003. Then mean squares will be 150.85. Once you divide this value by 3, the degrees of freedom for it, then this will be 295.87. Once you divide 3550.45 by 12, the degree of freedom for it. And for you to get your F calculated, all you have to do is to divide your mean squared treatment by your mean squared within treatment. Your mean squared between treatments by your mean squared within treatment, and that will give you 0.51. Once you divide this by this, that is 150.85 divided by 295.87 will give you 0.51. Now, once you've gotten this, what then should you do? You move over to step 5, the final step. In step 5, you take your decision. You make your decision or your conclusion. And what would it be? Since F calculated, our F calculated, which is 0.51, is clearly less than our F tabulated, which we earlier got to be 3.49, we reject our null, and we do not reject H naught. So that will be our conclusion. Why are we making this conclusion? It is simply because for us to reject our null hypothesis, it must happen that the F calculated value should be greater than the F tabulated value. But if it happens otherwise, you do not reject your null hypothesis. And that brings me to the end of the second problem, which is a problem on one-way Anova on balance. That being said, let's go to the third problem. Remember, in this class, we are discussing 4 problems, like the thumbnail says, 1 and 2-way Anova, balanced and unbalanced. So the first problem we solved, please smash a like on the video once you get into the class. The first problem we solved was a problem question 1 on one-way Anova balanced. The second problem we've solved is a problem on one-way Anova unbalanced. The third problem, question 3, that we are about to solve is a problem on two-way Anova balanced data. So, looking at the problem, let's read. The table below shows the yield per acre of 4 different plant crops grown on plots treated with different types of fertilizer. Determine at the 0.05 level of significance whether there is a significant difference in the yield per acre, 1, due to fertilizer, and 2, due to crops. So the data we've been presented is as follows. We have our treatments, fertilizer A, fertilizer B, fertilizer C, while we have our blocks. In this case, since it's a two-way, crop 1, crop 2, crop 3, crop 4. So in this particular problem, we are using crops as blocks and fertilizers as treatments. So let's now move over to solving this problem. So let's begin. Now, for us to begin solving the problem, let's see. The same steps we took is the same steps I'll recommend. The only difference is that in a two-way Anova, you would end up having 2 sets of hypotheses. Two null hypotheses will be needed, and 2 alternative hypotheses will be needed, because in this case, one hypothesis, that is one null hypothesis, will be one that calls for no significant difference between treatments, and the other null hypothesis will be one that talks about no significant difference between blocks. For the alternative, you would have two alternative hypotheses also. One alternative hypothesis will talk about no significant difference between between treatments, and the other alternative will talk about significant difference between blocks. So the first step, just like we've used 5 steps previously, I would also recommend 5 steps here to solving the problem. So step 1 state your null and alternative hypothesis. Okay, so state them. Now, this is what I'm going to do. Since it's a two-way problem, please pay attention. I'm going to write H0 1. I'm using this one to make you know that I'm discussing or writing out the first null hypothesis. So this is read as the first null hypothesis. And for this particular problem, since fertilizers are taken as treatments and crops are taken as blocks, it means the null hypothesis here will be the first null hypothesis will be that the effect of fertilizers are the same, meaning that there is no significant difference in the effect of fertilizers. So another way of saying it is that the effect of fertilizers are the same. So then you would come over to the first null alternative hypothesis. If the first null hypothesis is saying that effects of fertilizers are the same, the first alternative hypothesis will be telling you that effects of fertilizers are not the same. Okay? So what have I done? This is a two-way problem. I have taken the first set of hypotheses. Remember, there are two sets of hypotheses. Now, once you do this, let me put this way. I will come over to the second set of hypotheses, H0 2. So H0 2 is the second null hypothesis. And remember, that will be for blocks. And we are using crops as blocks. So this will state the effects of crops. Effects of crops are the same. While H1 2, that is the second alternative hypothesis, will state that effects of fertilizers are not effects of crops are not the same. Okay, so I'll quickly correct that with my correction pen. Let that dry up. I'm going to correct that. So the second alternative hypothesis will state that effects of crops are not the same. Now, once you are done stating your hypothesis, you would move over to step 2. So that was step 1. I will move over to step 2. Okay, so what do you do in step 2? Like we did earlier on for the one-way Anova problems, you would define your critical region. Define your critical regions. Okay, here, please take note. We are to reject H01 if F1 computed is greater than F1 tabulated. Okay? In which case, that is where F1 tabulated for short is the same as F1 in bracket A minus 1, okay, comma, A minus 1 and B minus 1 at alpha level of significance. And this will give you F1 at 3 minus 1, since there are three treatments, and this will be 3 minus 1 times 4 minus 1. There are 4 blocks at 0.05. So this finally will give you F1 at 2, 2 times 3 will give you 6, 0.05. Now, if you check out this value in your table, like I've done, if you check out this value in your table, that is 26, 0.05. So this is an excerpt from my F distribution table. Now, this is 2 at 0.95 under 6 is 5.14. Okay, so this will give you 5.14. Now, this was for the first null hypothesis, the critical region for the first null hypothesis. So let me put this back since that is dry. Now, you would have also, we reject H02, the second null hypothesis, if F2 computed is greater than F2 tabulated. Okay? So this will be the critical region for the second case, for the blocks. And that would mean where F1 tabulated is F1 at B minus 1, A minus 1, B minus 1, alpha level of significance, which will be F prime A and B minus 1. There are 4 blocks, so you have 4 minus 1, and 3 minus 1, 4 minus 1 at 0.05, and this will give you F prime F2, please. This will be F2, this will be F2, this will be F2, point of correction, because we are talking about the second F value. So this will be F2 at 3, 6, 0.05. Okay? Now, at 0.05, 3, 6 at 0.05 again, I had already checked that value out. It will give me 4.76. So this will be 4.76. I'm going to write 4.76 here. And that concludes step 2. In step 2, what have we done? We have obtained our critical regions. So I'm now going to move over to step 3. What do we do in step 3, guys? In step 3, what we do is to compute the sum of squares. So I'm going to compute the sum of squares. I'm going to compute the sum of squares. Now, this would mean, in this case, for a two-way Anova problem, computing V, the rows being my treatment, the columns being my blocks, and V error for the variation within all the coming from all the observations. So this will give me, for V, I will be computing with from I equals 1 to A summation, from J equals 1 to B summation, Xij squared minus double summation in bracket to A to B from I equals 1, J equals 1, Xij all squared all over A, B, where A represents the number of treatments and B represents the number of blocks. So this will give me 40 squared. If you start adding all the observations, the square of all the observations, 30 squared, that's along each row and column, you would end up having this 60 squared minus, if you sum all the observations in the spread, you are going to have 642. So this will be squared all over 3 times 4. There are 3 treatments, 4 blocks, so that will be 3 times 4. And that will give me a total of 36104 minus the square of this will give me 164 divided by 12. So simplifying that gives you 36104 minus the average, of rather 412164 divided by 12 gives you 34347. Okay, and that simplifies to 1757. This is the final value you would get for your total degree and total variation, and that will now bring me to the next. Now you are going to compute VR. VR will be for the variation between treatments, and that will be computed with this formula: to A to B, I equals 1, J equals 1, X bar I dot squared minus the correction factor we had earlier on, which is this summation to A to B, I equals 1, J equals 1, Xij all squared all over AB. Now, this would mean for this, all you have to do is, let's go back to the problem How do you do that? These are the treatment. Remember, the treatments are taken to be fertilizers. So I'm going to take 40, add it to 50, add it to 30, add it to 45, and divide by 4. That will give me the mean of this treatment. I'm going to do same to get the mean of this treatment for B. This plus this plus this plus this divided by 4. This plus this plus this plus this divided by 4. Now, in each treatment, I have 4 levels. So what I'm going to do here, since there are 4 levels for all of them, I'm going to write out 4 times the square of each mean. So for the first treatment, I have 41.25. I'm going to square that value. For the second treatment, I have 51.275. I'm going to square that value, okay? Plus, for the final treatment, I have 67.50. I'm going to square that value and subtract my correction factor 34347 from the result I get. Now, this will give me 35743.5 minus 34347, okay, and that will give me 396.5 as my V treatment, the variation between treatments. So once you do that, you now go to blocks. The variation between blocks can be computed using the formula to A to B from I equals 1, J equals 1 of X dot J bar all squared. Now, this is you getting the mean of each block and subtracting the correction factor from them. So this is what I'm going to do to A to B, I equals 1, J equals 1, Xij all squared all over AB. And this would mean 3. Now, in each block, there are 3 treatments, okay? So I'm going to use 3 since it is balanced and multiply the mean of each block. The mean of block 1 for crop 1 is 553.33 all squared. So I'm going to take the square of each mean. For the second block, I'm going to square the mean. For the third block, I'm going to square the mean. For the fourth block, I'm going to square the mean. So I have 4 blocks, and I've taken their means all squared, and I'm going to subtract the correction factor 34347, and that will give me 391, okay, mine point 0.3868, okay. So that was what I got, and I'm going to subtract 34347 from that value. Now, once you do that subtraction, you end up having 44.3868. Now, how well you approximate depends on you. Whichever way, your answers will not diverge too much from what others are having. So depending on the approximations you do, your answers may slightly vary. So once I've gotten my variation between blocks, I'm now going to take the error, the error variation. So that will be V minus VR minus VC. Remember, when you add the variation between treatments to the variation between blocks and to the variation in the total setup or the error setup, you are going to have V, the total variation. So this will give you 1757, what we obtained for V, as you can see, minus the result we obtained for VR, 1396.5, minus the result we have just obtained, 44.3868. And if you simplify, that will give you 316 rather 0.1132. So now this concludes step 3. We will now move over to step 4. So in step 3, we have computed our sum of squares. In step 4, what do we do? In step 4, we will set up our Anova table. So let's set up our Anova table quickly. Now, for the Anova table, please take note. This time around, you are not going to have 3 rows like in the case of the one we Anova. Rather, you would have 4 rows because we now have blocks among the rows. So I'm going to put this. So this will be row 1. This will be row 2. This will be row 3. and this will be row 4, my final row. Okay, so for columns, you will still have the same number of columns. So I'm going to have column 1 for source of variation, column 2 will be for degrees of freedom, column 3 for sum of squares, and column 4 for mean squares, and column 5 for my F computed. So I'm going to put here source of variation. I'm going to put here degrees of freedom, or you could just put DF for short. I'm going to put here sum of squares, or SS for short, and I'm going to put here mean squares, or MS for short. Okay, mean squares, and here I'm going to put my F calculated or F computed, the way I like calling it. You may like to call your own F ratio, you will still be correct. So the source of variation will be coming from between treatments. It could come from within between blocks. These are my sources of variation. So variation can come from between treatments. It can come from between blocks. It can come from error that is from within the treatment and within blocks. Within treatment, within blocks amounts to variation for error, and this will be total variation. Now the degrees of freedom for treatment will be A minus 1, which is 3 minus 1, giving you 2. The degrees of freedom for blocks, the number of blocks is B minus 1, will give you, there are 4 blocks in this problem, 4 minus 1 will give you 3. Now the error, for error you have the number of, the degree of freedom for blocks, or for treatment, times the degree of freedom for blocks, which is A minus 1 times B minus 1, that will give you 2 times 3, which is 6. Now the total degrees of freedom will be AB minus 1, or just simply add these 3. So AB minus 1 is 3 times 4, which is 12, minus 1, giving you 11. So this is more or less saying 12 minus 1, giving you 11. Now the sum of squares, let's write our sum of squares. For between treatment, we got it to be, that is our VR, we got it to be 1396.5. For between blocks, we got it to be 44.3868. For error, we had it to be 316.1132. And for total, we had it to be 1757. So I'll just quickly write that out. Then come over to mean squares. For mean squares, please, I hope I'm talking to you guys. Those of you online, live, please could you just indicate so that I know that I'm actually talking to people. Some people are actually listening to what I'm saying. Okay. For those of you that may be watching this video later, please take pains to look through everything that was done step by step. We are putting them in steps so that you easily can understand how to solve problems in Anova for one-way Anova, two-way Anova, balanced data and unbalanced data. So that's what we are doing, and we are taking them problem by problem. So we are in the third problem. Let's now go over to the mean squares. The mean squares for between treatment will be this, the sum of squares for between treatment divided by 2, the degree of freedom for between treatment, and that will give me 698.25. That is using this to divide this. Rather using this to divide this. So you end up having, for this one, you would have 14.7956. That is using this, dividing this by this. That should be the correct language, okay? So for the error, the mean squared error, you would use 6 to divide this value, the sum of squares, and you would have your result to be 52. You have it to be 52.6855. Now, that gives us, for our F calculated, we are going to have 13.253, and we are going to have 0.281. Now, how did we get these values? Your F calculated in this instance for treatments will be the mean squared error for treatment divided by the error. Okay, the mean, that's the mean square for treatment divided by the mean square for error will give you this value. The mean squared for blocks divided by the mean squared for error will give you this value. Okay, thank you very much, Christabel. Thank you very much. So I hope you can hear me clearly. I really appreciate you being with me throughout. So once you are done with step 4, we now move over to step 5, the final step for this problem. So step 5. Okay? So let's move over to step 5, the final step for this problem. So give me a moment. Okay. Now, moving over to step 5. What are we going to get in step 5? In step 5, we are going to take a decision based on the result of our problem. Please, I hope those of you watching, you understand what I'm explaining and you can hear me clearly. Those are two things important to me. One is understanding, two is hearing me clearly. Okay, please, can you hear me clearly and are you following? If you are, please indicate. Thank you very much. So F1 computed, since F1 computed, which is 13.253, is greater than F1 tabulated. Our F1 tabulated, we got it to be 5.14, and our F1 computed from the table is 13.253. Now, since the F computed is greater than F tabulated for treatment, we would reject the null hypothesis. So we say we reject the null hypothesis. But statistically, most times when we reject the null hypothesis, we don't jump into accepting the alternative. So we simply say we reserve judgment, okay? Because an increase in sample size can affect the result, can influence the result or the outcome. So we usually would go with reserving judgment, okay? So we conclude here, so the effects of fertilizers, we conclude that the effect of fertilizers are not the same, okay? Are not the same. So that will be our conclusion for treatment. Now, moving over to blocks, let's look at the F computed for block. Is it greater than the F tabulated for blocks? That's the question we ask. So we would conclude also, since F computed, that is in this case F2 for blocks, which is equal to 0.281, is less than F2 tabulated, which is for blocks, which we obtain to be 4.76, we do not reject the null hypothesis. So we do not reject the null hypothesis. Okay? Since the value of computed is less than the value of tabulated, we do not reject the null hypothesis H not 2. So we conclude that effects of crops, we conclude that the effects of crops are the same. So we do not reject the null hypothesis. So we conclude on what the null hypothesis had earlier stated, that the effects of crops are the same. Now, that question number 3. So question number 3, guys, was a problem on two-way balanced data, two-way Anova balanced data. So let's now move over to the final problem I'll be solving tonight, which is on two-way unbalanced data. So two-way unbalanced data. How do we go about that? Let's see. So look at the difference in the average weights of detergent. 1 due to the detergent, and 2 due to our lines, the product. Now, it could be that the makeup of detergent, the chemical components, or the weight, the type of detergent in treatments, and arranging the product. So in step 1, what do we do again? If you remember the drill, you should know the drill by now. Step 1 in the Anova problem requires that you state your null and alternative hypothesis. Now, this is also a two-way problem, so we are going to hypothesis. Somebody should answer that question in the comment section. How many hypotheses are we going to have? we are going to have two sets of hypotheses containing how many hypotheses altogether? Null and alternative. Okay, it's not really clear. From my end, it is very clear. Is it that blurry? Is it appearing blurry, Anastasia? Please let me know. Okay, so state your null and alternative hypothesis. State your null and alternative hypothesis. I'm going to get that done. Wow. Okay. Should I increase my writing? Should I increase my writing? Or the video is just not sharp altogether? Which one is the problem? Could you let me know? Please let me know. Should I increase the legibility of my writing, or it's just generally not clear? So while I leave you to answer that question, let's state the null and alternative hypothesis. So H, yes sir. When you say yes sir, smart. When you say yes sir, what are you actually saying yes sir to, please? Could you make a statement? Should I increase? Is your yes sir referring to me in handwriting, the legibility of it? Is that what is making it not clear? Or, okay, currently the video is not clear, but not from the writing. Wow. Could that be network? Sorry about that. Sorry about that. Sorry about that. But was it clear before now? Was the video clear before now? Before now, was it sharp? Was it clear? Was it clear before now? Wow. I wish at the end of the video, when it uploads, it will be clearer. Well, let's make progress. So H not, this will be your first null hypothesis, and of detergents are not the same. Okay, so that will be my first null and alternative hypothesis, and I'm gonna group it here. So for the second, I'm going to put H. Yes, it was really clear before. Wow, but at the moment it's not clear anymore. Wow. Could it be network? Could it be network? Okay. So this will be effects of lines, production lines. Move over to step 2. Please, guys, those of you watching at the moment, has the video quality improved? Has it become clear now, or is still not clear? Wow. So let's proceed anyway. So the next step, step 2, I'm going to define, we reject H1 if we are going to reject H if F1 computed is greater than F1 tabulated. Okay? Where the F1 computed, or F1 tabulated rather, the F1 tabulated will be equal to F1 at A minus 1. Now, this is what I want you to really know. Please, for the unbalanced case, do not use that degree of freedom you used earlier on for the balanced case for the 2. Rather, use N minus alpha. So this will give you F1 at 5 minus 1, since you have 5 treatments, and you have here 16 minus 5 minus 4 blocks plus 1 at 0.05. This would reduce to F1 at 4 degrees of freedom, comma 8, 0.05. Now, if you check this in the table earlier on, that is F148. This is 4. This is 8 for the second degree of freedom. This is 4 for the first degree of freedom. It is going to give you F48 under 0.05 gives you 3.84. Okay, so I'm going to write here 3.84. Now, I'm going to come over and say reject also for the second null hypothesis. Reject H02 where we actually had problems with the clarity of the video. Okay, so sorry for any inconvenience, or sorry for that. I may also put you guys through. So this will be F2 tabulated equals F2 at B minus 1, in this case for blocks, N minus A minus 1 times B minus 1 here. You may get it wrong. So rather use this. This would amount to, for short, this would amount to 3, 8, 0.05, which gives you 4.07. This is the value you are going to get, just like this. Okay, you are going to get this value, that is 3.8 under 0.95 will give you 4.07. Now, that will conclude step 2, and you would move over to step 3. Now, in step 3 is where you compute your sum of squares. So let's quickly compute our sum of squares, so that VR, VC, and V error. Now, you start with V from all squared, okay? Now, I'm going to subtract my correction factor, summations. Has it improved or is still the same? So this will give me N, and this will be equal to, up to the very last, which is 12 squared and 9 squared, okay, minus this 4 divided by 16. If you add properly, and you are going to have 112 minus the average 1 percent, which 1 x bar I dot squared minus summation A B L I equals 1 J equals 1 X I N. Now this would require you, just like we did in the one-way Anova unbalanced, you would use the number of observations in each to multiply their respective means. So I'm going to put here, I'm going to put 4 times 10.50, the mean 4, the number of observations in treatment 3, times 9.25, the average of all observations in treatment 3, plus 3, the number of observations in that treatment, times 9.33 all squared, plus 3 times 8.00 all squared. Okay, or I'm going to subtract 1369 from them. So when you sum all these are the means. Sweet? Please, is network on your end? The network is bad from your own end. Sorry about that. I'll check when the video ends. So now this will give you, if you simplify further, let's wrap up. This will give you a total of 138 bar squared dot J minus double summation to A to BL I equals 1 J equals 1 bar n, and this will give you 4. Now in this case, you will go to the blocks. The first block has 4 observations, and the mean of that block, when you add all the observations in that block and divide by 4, that will give you 9.25. Square that observations in the fourth and final block times the mean of that block, 10.67, all squared, minus 1369. Okay, that will now give you minus 11.8967 minus 8.7967, and this. Okay, so once you are done with getting your sum of squares, you can now go to step 4. So in step 4, you set up the Anova table. Set up the Anova table. Okay, so I'm going to quickly set up my Anova table. Remember, this is a two-way Anova, so I'm going to have 5 with a total of 3. I'm going to split them now. This will be variation. The second will be for degrees of freedom. The third will be for sum of squares. The fourth will be for mean squares, and the last will be for my F calculated. So I'm going to put here source of variation from between treatments. So I'm going to put that here, between treatments. The second source of variation is from between blocks. So for the degrees of freedom, you are going to have total degree of freedom, and that will give you 16 minus 5 minus 4 plus 4 minus 1, giving you 3. And for between treatments, you are going to have 8 minus 1, which is 5 minus 1, giving you 4. Sum of squares, you had 11.8967. For between blocks, we had, if you divide this by 4, that is your sum of squares between treatment by 4, you are going to get approximately 2.9742. decimal place 2.31.06. This calculated value. So we're going to compare them now to end this problem by making a decision. So step 5. Step 5 is where we make our decision. 0.06 null hypothesis. We do not reject the null hypothesis. So what would our over blocks? For blocks, you will notice no reject here. It was H1. Okay. What hypothesis are we rejecting here? Or H not 2, not reject, not hypothesis, not 2. And we conclude being part of the live class for almost 2 hours. Please give yourself a round of applause. You've really tried. God bless you for staying tuned to the channel. And for those of you who will be watching this video subsequently,